All right. Welcome, students. Welcome back. So I would have recorded this um, basically passive questions working out already, but there were some issues with the audio. So what I'm doing now is simply going to just have a voice over a video, basically, right? So that you can see what happened there. I mean, I'm a little bit busy these days, so that's the reason why I haven't got a chance to done it. Well, I didn't get the chance to do it previously, right? But these questions that I've selected are questions uh, that are essentially going to come on the exam in a sense. They would involve some of the broad topics, right? Capacitors and all of that kind of stuff. So this lesson here is really geared towards that. So I hope that this is going to be beneficial to you. And the first question that we're going to look at here is a capacitor question. All right, perfect. Now, as you can see on the screen, it is asking us to define capacitance. Right, so this is now the time for you to start thinking about what capacitance really is. As the word suggests, capacitance, you know that has to do with a capacitor. And right now, these are basically, all right, that is generally the diagram for a capacitor for the most part, right? The reason why we have those those two long lines coming down has to do with the fact that um, capacitors are really made of parallel plates, right? And if you know how capacitors work, right, those two plates, they are going to be charged up. And by what we mean charge, one side is going to gain positive charge, the other side is going to gain negative charge. Whenever that occurs, you have a potential difference, right? So by definition, capacitance, simply put, is the amount of is the charge stored per unit potential difference, right? So that's just simply put of how capacitance is defined as, and it's a one mark question. So it is the charge stored per unit potential difference or per unit voltage, all right? So nothing hard there to understand about capacitors for the most part in terms of the diagram, right? So once you see that diagram, you know that it's a capacitor, okay? All right, so the question continues here talking about a capacitor with a capacitance of two, well, 2,100 microfarad is charged until the potential difference between its plate is 6 volts. It says here determine the charge on one of its plate. All right. So we want to find out the charge that is on the plate. Now you must understand that most things in physics have some formulas to do with it, right? And in this case here, we're going to see the formula coming up very soon. So capacitance is equal to Q, which Q talks about charge, divided by V, which is the potential difference. And as you can imagine, the unit is farads, right? So it means therefore that anything dealing with capacitors is going to have this unit. Now, very important thing to note is that when they give you the capacitance here, you have to factor in the micro that is attached to the unit, because micro is not the unit completely for capacitance. So you have to now take that into the calculation, and you will see that shortly, right? So farad is the unit. So when we go ahead and use the formula here to find the charge, right, then you would have to take into consideration the micro, right? And we know that micro means times 10 to the to the minus 6, right? So since we know that capacitance is equal to Q divided by V, and from the definition that is what was stated, that capacitance is equal to C divided by V, right? Then we can transpose the equation so much so that we get Q. So Q in this case is going to equal to CV. All right. So if we go ahead and do that, then we can get the value, and I'll just show you shortly what the answer here would be like. So as you can see, by way of transposition, Q essentially is going to equal to 0.0126. I wrote, so I see where I wrote volts right here. This is not volts. Sorry about that. This is going to be in coulombs. All right. So this is going to be in coulombs and not volts. So that's a typographical error there. I hope I did correct it further on. Let me see if I did. So I still made the error there. So it's not volts, but it's actually coulombs. All right. Possibly I think I found out. Yes. So yeah, it's obviously coulombs. Sorry about that. So we now continue here, and the next question is to say, you know, what would be the current stored by the capacitor? As you can imagine, capacitors store energy, right? And in order for us to know how much energy the capacitor stores, we have to understand the graph for a typical capacitor question for the most part. Now, if I were to go ahead, right, and transpose the equation, right? If I transpose the what do you call it now? If I transpose the Q equals CV, well, not say transpose, but if I make C becomes the what do I call it now? All right, never mind. Don't worry about that. But what are you gonna see here? We're gonna plot a graph, you see, of volts versus charge, right? Voltage versus charge. That graph is going to give us a straight line graph because of the fact that, you know, volt and charge, they are directly proportional. So if you increase the voltage, you expect to get an increase in the number of charge that is being stored on the capacitor. So what you're going to see here is that the area underneath the graph, right? The area underneath that graph is going to provide us with the energy that is being stored within the capacitor. All right. And if you know anything about the area underneath the graph, you're going to see something spectacular here. Just give me a second. Right. So there's the graph that I was telling you about. So let's see. Yeah. So you would get that type of a graph, right? So Q is obviously our X variable, V is our Y variable, as you can see on the graph. Now, if I were to find the area underneath the graph, right, then that would present itself to be the amount of energy that is stored in the capacitor. And the area underneath the graph is going to be the area of a triangle. And that now, how we find the area of a triangle is half base, right? Right, half base times the height. Now, what is my base? My base is Q. What is my height? My height is V. So if I say energy, right, I could say energy is equal to half Q times V. And once I do that, I will be able to find out the amount of energy that is stored in the capacitor. Right? So, and in this case, the unit, obviously, because we're dealing with energy, the unit is going to be energy, right? So that's going to be the unit. So by way of this calculation, if you put in the values, you're going to see that the energy, and in some cases, guys, we use U to represent the type of energy that is stored in the capacitor. But you can just simply write out energy if you want. But if you see U, then you know we're talking about the energy that is stored within, right? Now, mind you, when you're revising, there are going to be several equations that you can possibly use to determine the energy that is stored within the capacitor. But the most basic one has to do with half Q times V, right? And if you're paying attention enough, then you could substitute for Q, right? So Q is equal to CV. So you could possibly go ahead and get a different equation that says U is equal to half C V squared, right? But we're not really doing that right now. But I'm just letting you know that there are different equations. But all the other equations that we'll talk about will come from this basic equation. All right. So at this point, we can see that the amount of energy stored is 0.0378 joules. All right. That's the amount of energy that's stored. Now, we move on from that question to part B. It says that a student set up a circuit shown in figure 1, and after closing the switch S, observe how the voltmeter reading varied with time. It says that a graph of data obtained is shown in figure 2, noting the volt meter reading decreases as time lapses. The student proposed the hypothesis that the voltmeter reading is inversely proportional to the elapsed time, t. So here we're seeing something spectacular occurring here. I mean, we have a capacitor, we have a switch, we have a battery, we have a resistor. So the switch is going to be closed, right? And we're seeing where that the voltage across the resistor is going to be inversely proportional as time lapses. What that tells us, ladies and gentlemen, is that as the capacitor becomes charged, right, it now decrease the amount of voltage that would be recorded across the resistor here, right? Because technically speaking, the capacitor is going to store as much charge that the EMF is providing. So technically speaking, the capacitor is going to store up to the amount that the EMF has, once the capacitor has that capability. So from a graphical standpoint, we're seeing a decreasing or exponentially decreasing graph, which, technically it's not saying that the capacitor is being discharged here. However, it's just simply showing us, that the voltage across across the resistor is essentially decreasing as the capacitor charges. So that's a thing that you must understand. So it's just a graph here, and all they just want us to do is to complete this table. It says test your hypothesis by taking the data from the graph to complete table 1, and then plot a graph of 1 upon V against T on the graph we were provided. So you're going to go ahead and do that, and obviously read the information from the graph. So that is essentially what we're doing here. So once you find that point, you read it, right? And that's going to give us some value here of about 4.8, I believe, or 4.7. Let's see. Right? So that's what we're doing. We're reading our corresponding X and Y values at the same time, or coordinates, and we're going to just do that all right along the way until we're finished. And then, ladies and gentlemen, we'll just go ahead and find 1 over V, right? So 1 upon V is just simply the inverse of V. So once you do that, then you just fill out the table, all right? So there's nothing hard right there to do. And then from there, now we're going to plot the graph and see what the relationship is. Now I must point out to you, try to see if you can find this particular question. I think there's a portion of it that I would have left out, not intentionally, right? But I believe that the what you would see now, that 1 upon Vt versus T, let me say this again, so that 1 upon V versus T, right, is going to possibly give you a straight line graph. Because if you look at the data compared to So if you look at time and 1 upon V, you're seeing that the values are increasing proportionally, right? So that's something to note about the data. So one of the things that you must understand, ladies and gentlemen, is that you should analyze your data as you get the graph so that you can understand the information that will be provided or given in such scenario. All right. So this would have been somewhat of the graph that I was plotting here. You guys can go ahead and definitely do that. I mean, technically, whenever you're plotting your graph, you need to choose an appropriate scale, ladies and gentlemen. So much so that all the values in the table can be accounted for. Let me see what the values here on the, so the last value for time is 90, right? And I believe the last value for 1 upon V was what? 0.6. So it therefore means that when you do this graph, I mean, I could have chosen a better graph or a better scale for this axis, right? But it could work for now, you follow me? Because it actually covers at least, more than 50% in a sense, right? But you can choose a more appropriate graph. And it's important that your scale is on your graph. You understand? All the labelings, your time, the title, of course, label your x-axis and your y-axis, right? So you have to indicate that. So like how you see in time right here, and you're seeing the units in brackets, you must do those things, okay? So you're going to get obviously a straight line graph. If you do these things, well, I don't think it's necessary. There was probably some discrepancy maybe here, but at the same time, I believe you should be getting a straight line graph. Maybe I did plot something incorrectly here. Let me see if I did correct it. Right. So yes, there was something that was wrong here. So correction to that. So it's now going to change something about this value. All right, it's going to change something about that value. But at the same time now, so this is more of a better data that we're seeing here. So there was a little bit of a challenge with that graph, but I would have corrected it, right? So this somewhat, so guys, remember it's a line of best fit. So please do not draw your ruler going like this and then connecting it and all of that kind of crazy stuff. You just need to find a line of best fit. Now, I was having a little bit of a challenge when it comes down to the line of best fit for this graph, but what you must understand is that whenever you're dealing with the line of best fit, so let's suppose that you have 8 points, right? And when you draw the line of best fit, 4 of the points pass through the line. Now, what you must try to do is to make the other points become balanced on both sides. So you'd end up with having at least 4 points remaining that did not pass through the line. So what you now need to do is to ensure that 2 of those points are underneath the line and 2 are above the line, basically, right? To get a more sophisticated and best fit line, right? Now, if the graph had asked us to find the gradient, right, then you would select a point on the line that wasn't originally plotted on the graph, right? So that's how you go about doing those key things, right? So I'm just making a little bit of adjustment there to essentially, make it become a little bit more of a best fit type of thing, right? So I believe that is the best that I could have done with this graph. Now I must point out something to you. When you see this point over here, so this point is an outlier, okay? So it means that it's far away from the plot of the data. You don't need to try to force your line through this point. Now also, there are times when your line will not start from 0, so there's no need for you to start the line from 0, go all the way up, right? You just need to draw the line, close to where the data starts and close to where it ends. So basically, you can stop here and you can stop right here. So don't try to extrapolate the graph too far out, because that can run you into problem when you're doing certain calculations. All right. So please, that's that on that part. Now, as I said, with this question, maybe there's another part to it. So you can go ahead definitely and check out that thing. Now, moving along here, these are stuff that you might can see on the exam paper, talking about Kirchhoffs two laws, right? When it comes down to Kirchhoffs circuits, right? We must understand what Kirchhoffs is really saying. So the two laws that governs Kirchhoffs, one is Kirchhoffs current law, right? Or we could say Kirchhoff's first law, or we could simply say KCL, right? So that's the first law that we know of. Then Kirchhoff's second law simply speaks to voltage basically, right? So let's see what Kirchhoff's first law says, right? So Kirchhoff's first law really states to us that the sum of the current, right, entering a junction is equal to the sum of the current leaving the junction. So as you can imagine, we have a junction right here, right? So as the current flows, it's going to come to this junction. When it reaches that junction, it's going to divide itself, right? So some current is going to flow down, some is going to flow to the next resistor across. So simply put, if I were to, so what Kirchhoff's first law really links with is the principle or the conservation of charge. What that simply tells us is that if I start out with 10 coulombs of charge, it means that when that 10 coulombs reach the junction, it's going to divide up, right? So when it's finished divide up and everything, and I add up back all of what was divided, I should get back the same amount that I would have started out with. So when I add up I2 and I3, it must add up back to 10 because that's what I started out with. So that just speaks to the fact that there is conservation of charge throughout the circuit. So in this case, we're saying that the sum of the current entering the junction is equal to the sum of the current leaving the junction. So I1 is the current that is entering the junction. I2 and I3 is the one that's leaving the junction. So we'll just simply sum that up. Okay. Now, as we continue here, so yes, conservation of charge. Then, of course, when it comes on to Kirchhoff's second law, right, that law now speaks to Kirchhoff's voltage law, basically. And what that really tells us is that within an enclosed loop, ladies and gentlemen, and an enclosed loop is simply, an enclosed area where the components are connected behind each other. It tells us that the sum of the EMF in that loop is equal to the sum of the potential drop across each component, right? So each of the components that are connected in one loop will essentially have what we call a potential drop. And with that being said, we now have to factor in that we really have to factor that in. Right? So in most cases, you will see more than one loop, right? So the first thing for you to do is identify the loop when you get a question like this, right? So that's going to be my first loop. Whenever you're identifying your first loop, you need to show the direction through which the current is going to flow, right? But I'm making a slight modification to this circuit, right? And the reason for doing this is so that you can understand something, because there are times when you'll see more than one EMF connected in the circuit. And there's a specific way that we go about adding the EMF when they are connected in a simple circuit. So here I'm going to add another EMF, which is basically a cell, right? Power source, obviously. So that's my second EMF. Now, there are certain ways. So if I look at the circuit and I see that the positive terminal of one of my EMF is connected you know, not directly but connected to the positive terminal of the second EMF, then it simply means that these two EMFs right here, I will have to subtract them. All right, I will have to subtract them. So what I just did a while ago was to just identify the loops. I have loop A and loop B. All right, so let's just watch and see here what's going to happen next. So yes, as I was pointing out to you that I have two EMFs. So remember Kirchhoffs notes, second law says the sum of the EMF. But you must understand, when are we going to sum these EMFs together? Follow me, right? Because it's important that we understand something here, and I think you're going to see it very soon. So what I'm writing now is just Kirchhoffs. Sum of the EMF is equal to sum of the potential drop across the component, right? All right, so we have that. So I just relabeled the EMF E1 and E2. Right? All right. So I'm really sorry that the recording didn't record the voice at first. I mean, because there's obviously might have been some other stuff that I would have explained here, that I don't remember that I would have, said earlier. But to basically look at what we're doing here, from the mere fact you see the positive terminal, right? Um, it doesn't have to connect directly, because as you can see, there's R1 that is connected in between. But from the mere fact you see that both terminals are kind of like facing each other, so like the positive terminals are facing each other, I have to subtract them. If you go ahead now and see the circuit, where the positive terminal is connected to the negative terminal, then that is when you go ahead and you subtract them. All right. So that's really what is taking place here. So to just finish up this, I'm basically saying E1 minus E2 is equal to the sum of the EMF, or the potential drop across R1, then the potential drop across R2. Now, as you can see that the current flowing through R1 is I1, and the current flowing through R2 is going to be I2, because once you reach a junction, there's going to be a different current flowing there, right? And what I should have done as well is to show you that I3 would be flowing through this side as well. So I should have identified that. All right. So that would complete that aspect of that. The question continues, right, to talk about the distinguish between the EMFs and the potential difference of a cell. Right, that is very important for us to understand. Now, the EMF, right, is obviously what we call the electromotive force, and that is essentially the maximum amount of energy that each charge, in a circuit will receive from the EMF, right? Or from the power source, basically, right? So the maximum energy by the total number of charge will basically tell you the EMF for the most part. So before you connect the battery into the circuit, right? That voltage that the battery has is basically the EMF. So it is essentially the maximum amount of energy that each charge, right, that is going to flow around the circuit will get, basically. Now, as it pertains to the terminal PD, which is the terminal potential difference, whenever you connect the battery within a circuit, right? And before I continue that, Kirchhoffs law is based on the conservation of energy, all right? So when it comes down to the terminal PD, from the mere fact you connect a battery in a circuit, right? The voltage that is measured at the terminals, right, will be what we call the terminal potential difference. Now, in most cases, you will realize that the terminal potential difference is lower than the EMF. Reason being is that there is what we call an internal resistance inside of the battery. And what happens there is that some amount of the energy from the EMF or from the battery will be used to overcome that internal resistance. So that's the reason now when you measure that voltage at the terminal, it becomes of a lesser value by a small amount, right? So that just shows that there's internal resistance in the battery and that the terminal potential difference is simply that voltage that is measured across the battery once it is connected in a circuit, right? EMF, as I said, is before the battery is connected or the cell is connected, right? That now will be the maximum amount of energy that each charge can get, all right? So that is what this lesson was about. There is more to it, which I will post in a subsequent lesson, right? So I hope that it makes sense to you, and I will definitely, post that lesson, all right?